In the quiet lanes of the Milky Way, a modest star draws a tiny loop that should not be there. Gaia measures the tremor with patient precision. Ground spectrographs catch its rhythm in shifting lines. Light offers no culprit. Gravity answers instead, a massive silent companion. Gaia Bh3, the heaviest known stellar black hole in the galaxy. No flare, no jet, only a steady pull that rewrites what nearby space can hide. How does such weight form without a blast? Why does it refuse to feed? What other dark giants drift beside ordinary stars unseen until motion betrays them? The story unfolds from data to wonder, astrometric wobble, orbital truth, a companion's chemistry, and a census of shadows that may reshape the map of the Milky Way. Along the flat plane of the galactic disk, where lanes of dust thread between arms of young stars and older suns drift with unhurried purpose, the European Space Agency Gaia mission keeps its steady gaze. It measures positions on the sky with patience that feels almost geological, marking the tiniest sideways motions, the subtle wavering that betrays companionship. Most stars march in straight lines once their motion is accounted for an even pace through space, but every so often a path curves in a way the usual models cannot quite absorb. The sway shows itself as a periodic nudge that refuses to vanish when the data are folded and refolded. Analysts see a bright, otherwise ordinary star, its shape on the detector, clean its colour, well behaved, yet its path is not entirely its own. The centroids slide a little to one side, then back with a quiet regularity, like the surface of a pond that lifts and settles under the pull of something just beneath. The term astrometry sounds technical, but the act is simple at heart track, where a star appears over time and watch for deviations from a straight line. In this case, the deviations build a curve that carves out an ellipse, modest in scale, but firm in character. The wobble is not an instrument trick, not a harmonic from the spacecraft's gentle roll, and not a nearby interloper blending light in a way that fakes a shift. The star itself is moving, and it is doing so because something unseen shares its gravity. This is the moment when a routine catalogue line becomes a seed of wonder. The drift that once seemed like noise coheres into the drawing of an orbit. Period emerges from spacing eccentricity from the lopsided way the motion speeds and slows inclination from the tilt that changes how the ellipse projects onto the sky. It is all there in the points waiting to be read, the way rings in wood reveal seasons long past. From the astrometric sweep alone one can deduce a partner of consequence. The companion must be heavy enough to tug a bright star measurably, yet faint enough to contribute nothing obvious to the light. That pairing pushes the mind toward collapsed objects. A white dwarf can hide its glow, but its mass is usually more modest. A neutron star can weigh more, but often marks its presence with harsh radiation, or a whirling, flashing beam. A black hole offers a simpler promise gravity without light. The Gaia curve hints at such a presence, but hint is not enough. The next act calls for motion along the line of sight, the to and fro that folds into the star's spectrum. Radial velocity sounds complex, but it means something immediate as the star moves toward and away along its orbit. Its dark lines slide by tiny amounts toward blue and toward red. Large telescopes on desert mountains turn their mirrors toward the bright target, and the spectrographs behind them listen for this rhythmic slide. Night after night and season after season the lines creep and return, with the same period the astrometry foretells. Sky motion and line motion lock together, and the orbit gains depth. Now the ellipse has weight. From the way the visible star wanders in space, and along the line of sight from the period that ticks like a slow metronome, and from the tilt that only geometry can grant the mass function gathers itself. The math is quiet, yet the conclusion is loud. The unseen partner is not modest. It bears the heft of a collapsed core far beyond what a faint ember could carry. As uncertainties shrink under repeated observation, the distribution of allowed masses drifts upward and tightens. The team runs careful checks for blended neighbours, hidden light that might masquerade as a larger wobble. The sky field is clean, the photometry stable. The companion remains dark. Here is the moment when the system earns a plain name in a long list, Gaia Bh3, a title assembled by process rather than drama. The label does not change the star, yet the star feels changed by the label. It becomes a marker, a sign that an old assumption has been pulled into the open. For years, most confirmed stellar black holes in the Milky Way have betrayed themselves through hungry disks that blaze in high-energy light. This one whispers through a partner's gentle sway. The quiet makes the weight more striking. Without a bright disk or flares, the binary moves through space like any ordinary pair, keeping its secrets, unless one knows exactly how to look. The local neighbourhood is not famous for extremes. It is a region of the disk where star formation strolls, rather than sprints, where abundance patterns are a mix of older and younger histories. That a remnant with unusual heft should settle here, bound to a bright companion, asks a question of origin. Did a giant star collapse directly, shedding little mass, and lighting no violent outburst, leaving a heavy core in place, and a wide orbit largely undisturbed? Did the binary survive a birth with almost no kick, the kind of gentle fall that spares the partnership? The present orbit, read from Skian spectrum, appears stretched and stately rather than tight and frantic. The period is long by human measure, the eccentricity real, the inclination favourable enough to measure cleanly. These are not just numbers, they are a chronology. Wide orbits suffer less from tides and less from the fierce friction that feeds disks. A quiet life can follow a quiet death. If the companion star shows chemistry that leans away from iron and toward older patterns, that too would complicate the story. A metal pore surface can hint at an origin in a population that formed when the galaxy was younger, when stellar winds stripped less mass from giant stars, allowing heavier remnants to remain. But surfaces can be deceiving, altered by mixing or by past exchanges. The first section of this narrative rests with the detection itself, the simple statement that a bright, steady star cannot walk a straight line because something invisible holds its sleeve. That simplicity unlocks a larger possibility. If a single black hole can hide in a wide pair with no loud signal of accretion, then many more may do the same, tucked into orbits that only a mission like Gaia can weigh. The census of the dark, long predicted and long frustrated by selection effects, begins to take on shape. The most massive examples are not necessarily the loudest. They are sometimes the quietest, moving the most through pure gravity and radiating the least. A survey designed to map the Milky Way structure thus reveals its shadows. The data are mundane in their format, a scatter of positions, a series of line shifts, yet they open a corridor into a population that alters how the galaxy grows old. With the first wobble secure and the first orbit sketched, attention turns to the system's many puzzles, but for now the intrigue rises from restraint. In a sky full of light, the heaviest partner is the one that refuses to shine, and the way it chooses silence becomes the loudest clue. The curve that the European Space Agency Gaia mission traces across the sky is not a picture so much as an argument carried by numbers, a quiet claim that insists on being heard each time the catalogue is recalculated. A solitary star should move with a steady drift while drawing a small yearly loop from parallax as Earth moves around the Sun, and after both are modelled there should be stillness in the residual positions. Here there is an ellipse, smooth and repeatable, each point arriving in order like beads on a wire, and the ellipse refuses to collapse into noise even when the data are sliced by season, by detector, by scan direction, or by brightness. That persistence is the first statistical knot that will not loosen, and it drives the analysis toward an orbit rather than an artifact. Astrometry. The practice of measuring positions can be translated into mass, because gravity decides how partners share motion around a common center, but only if the light from the visible star is not secretly blended with the second luminous source. High contrast images look for a hidden neighbor, and none appears. The spectral energy distribution is tested for excess light at redder or bluer wavelengths, and it stays clean. The color and brightness of the visible star settle into the expected place on the diagram that relates color to absolute magnitude with no extra lift that would betray a second bright companion. The photocenter that Gaia tracks therefore behaves as the position of a single star, not the weighted sum of two shining stars, so the wobble must be caused by a dark partner that tips the balance of mass without adding light. Once that premise is secured, the orbit can be fitted in full. The period emerges from the repeated pattern of the ellipse. The eccentricity, which describes how stretched the orbit is, reveals itself in the uneven speed with which the photocenter sweeps the curve. The inclination, the tilt of the orbit relative to the plane of the sky, leaves a signature in the ratio of the short and long axes of the projected ellipse. The longitude of the ascending node, the place where the invisible line of the orbit crosses the sky plane, arranges the ellipse on the celestial sphere. Each parameter narrows as more data arrive, and with them a bound on the unseen mass rises from possibility to necessity. A crucial piece still stands outside the plane of the sky, and it comes from radial velocity, the gentle push and pull along the line of sight that shifts dark absorption lines toward red and toward blue as the star moves away and then toward the observer. Large mirrors and stable spectrographs measure that sliding pattern across many nights and many months until the rhythm of approach and retreat locks to the sky motion. With astrometry and radial velocity joined, the orbit gains depth and the mass function tightens. A faint white dwarf would be too light. A neutron star would often show itself through harsh emission, and even if quiet, its allowed mass would not reach the value demanded by the combined fit. The solution climbs into the regime of a black hole not by dramatic flares but by arithmetic that refuses to bend. The claim invites every imaginable escape route to be tested. Could a cloud of interstellar matter deflect the light and fake a shift? The pattern would not repeat so cleanly across years if that were true. Could stellar activity reshape the photosphere and bias the centroid? Activity signatures would correlate with line broadening and with photometric variability, but the light curve sits steady, and the spectral lines remain calm apart from the orbital shifts. Could the system hide a second very dim star that adds just enough light to trick the centroid by a small amount and thus inflate the inferred mass? High-resolution checks again leave little room for such a conspirator. Each alternative demands a coincidence of parameters that strains credulity, while the black hole hypothesis simply states that gravity is doing what gravity does. The numbers then reach for context. The distance is known from parallax, so the size of the orbit can be written in terms of ordinary space, not only angles on the sky. The period is long by human standards, the eccentricity is real rather than trivial, and the tilt is favourable enough that uncertainties do not explode. Put together, these elements define a wide partnership with a heavy dark member whose silence is as informative as any blaze. A disk that feeds would shine in high-energy light, but catalogues in those bands list no source at the position. Radio surveys show no loud wind. Even deep searches for a cool disk leave no convincing trace. The absence of emission is not a void in the story, but a character trait the black hole is quiescent content to shape motion without drawing matter in. That quietness forces the inference to rest on the geometry of the orbit, rather than the fireworks of accretion and geometry once settled is stubborn. With the orbit established, the focus shifts to the visible star itself, because its nature controls the luminosity and the mass that the models must adopt. The temperature and surface gravity extracted from the spectrum point to a star that is neither infant nor ancient, set upon a track of evolution that matches its brightness at the measured distance. Its rotation does not blur the lines beyond recognition, which aids the velocity measurements, and its chemistry hints at a metallicity that may sit lower than the local average, although that hint is modest and invites caution. If the surface carries fewer heavy elements, it might reflect an origin in gas that cools less effectively and drives weaker stellar winds, letting a massive progenitor shed less mass before collapse, and so leaving behind a heavier remnant. That notion, while compelling, opens more doors than it closes, because surface abundance can be altered by mixing and by past exchange within the binary. Even so, the theme persists. Numbers that do not fit a typical nearby binary are trying to tell a history that involved gentle mass loss and a birth that gave little kick. A violent birth would likely have shattered the system, or at least driven the orbit into a state that the observations do not support. Direct collapse of a very massive star offers a quieter passage, one that keeps the partner bound, especially if the orbit was already wide. The data do not prove that path, but they favour it by exclusion of scenarios that would have left louder scars. All the while, the comparison with catalogues imposes a broader implication. If a very heavy black hole can sit in a nearby wide binary and alert the astronomers only through a tiny sideways sway and a slow, breathing in and out of spectral lines, then surveys that prefer flares and bursts have been biased against exactly such giants. The heavier stellar black holes in the Milky Way may often be the least talkative. Gaia, designed to map the galaxy at large, becomes a census taker for the silent. Each parameter in the orbit of this system is a tally mark toward a large account of hidden mass, a count that will change how models of the galactic disk apportion gravity among light and dark. The numbers here do not fit the old expectation that only hungry black holes can be found. They fit a new expectation that the quietest heavy objects reveal themselves by the patience of measurement alone, and that patience is beginning to redraw the map of the invisible. Listening for the pull along the line of sight begins with a modest promise. If gravity ties two partners, the bright one must drift toward and away in time with the orbit, and that drift will slide its dark absorption lines a little toward blue and then a little toward red. The idea sounds fragile, yet careful practice makes it sturdy. At the European Southern Observatory, the Very Large Telescope settles its gaze, and the ultraviolet and visual Echelle spectrograph spreads the starlight into hundreds of orderly grooves. Each thin line is a witness to a chemical transition formed in the calm of the stellar photosphere. Each can be measured again and again until a rhythm appears. Observers take pains with the chain that leads from photons to numbers. They guide the beam through a stable slit whose temperature and pressure stay nearly constant. They record calibration lamps before and after the star so that the ruler on which the spectrum is laid does not expand or shrink with the night. They map out the faint fingerprints that the air itself places on the spectrum lines from water and oxygen that sit on top of the stellar lines, and they remove those marks so that the star can speak without an echo from the sky. They shift the entire spectrum into a frame that follows Earth around the Sun, and through space a barycentric correction that turns the terrestrial platform into a neutral stage. They then compare the cleaned, corrected spectrum to a template built from the same star on a quiet night, or from a model with the same temperature and gravity. The comparison is not a guess, but a cross-match of pattern against pattern, many lines together outweighing the noise that any one line would carry alone. The answer that emerges is a tiny velocity, not a single point, but a point with an error bar that reflects the honesty of the method. Night after night and month after month, the points gather until the slow rise and fall of the star's motion is obvious even to the skeptical eye. The cadence locks to the astrometric period that Gaia has already suggested. Where the sky path accelerates, the lines grow bluer. Where the sky path slackens, the lines grow redder. Sky motion and spectral motion entwine. And an orbit that once lived only in angles grows a depth that no parallax can mimic. The visible star is not a blur of noise. Its lines are narrow enough to resolve, which means its surface does not spin so quickly that the pattern smears into confusion. Spots and pulsations are checked for by reading how the line shapes change. A restless surface would distort the cores and wings of the lines in a way that does not repeat with the orbital period, but the profiles remain sober. The photometry holds steady as well, with no flicker that would betray a beating or flaring atmosphere. That calm gives permission to believe the velocity curve, the amplitude of the swing, the shape of the rise and fall, and the phase relative to the astrometric ellipse together pin down the hidden mass with a restraint that the sky path alone could not achieve. The orbit is long by human habit, yet compact in the language of gravity, a solemn sweep that takes years to complete, and that lingers at apocenter where motion is slow before bending inward to pericenter where motion is quick. The eccentricity is not extreme but real, a memory of how the pair evolved without tides being strong enough to sand their path into a circle. The inclination is neither face-on nor edge-on, but blessedly tilted so that the combination of sideways drift and to and fro motion speaks in full sentences rather than in hints. As the curve fills in, the mass function steps beyond the realm of a white dwarf. It paces into the territory where a neutron star might live, but a neutron star, especially a heavy one, often brings signs that it is there. It can pulse in radio waves or throw hard light if a trickle of matter falls in, and surveys that search those bands find nothing at the position and distance of this system. The allowed mass range then continues to grow until the simplest reading becomes the one that carries the least invention, a black hole that does not feed content to leave only a gravitational signature. The investigators do not stop at the simplest reading without asking whether trickery still lurks. Could a dim second star sit close enough that its light drags the centroid traced by Gaia, inflating the apparent wobble and mimicking a heavier companion? High contrast images in the near-infrared sweep the neighborhood for a tucked-away ember. The field proves clean. Could the spectrum hide a doubled set of lines that would betray a bright second star moving on a different schedule and thus swelling or shrinking the measured velocities? Cross-checks for additional line systems come back empty. What remains is the unadorned duet that the data demand. With both astrometry and radial velocity in hand, the distance from parallax converts angular sizes into real lengths, and the orbit can be drawn not just as a shape but as a path in space. The companion star circles the unseen mass with a predictable grace, and the center of mass sits closer to the dark object than to the luminous one. The silence in high energy light and in radio folds naturally into this portrait. The separation at most phases is too wide for steady streams of gas to jump from the bright star to the black companion. The wind that leaves the bright star is cool and slow, and calculations of capture rates predict a trickle too faint for current facilities to see. The black hole therefore lives in a state that observers call quiescent, a word that sounds passive but in this context is decisive. It marks a population that surveys built on fireworks will undercount. The companion star now stands as more than a pointer on a map. It is an index of time. Its temperature and luminosity combined with its distance place it on an evolutionary track that suggests maturity but not senescence. Its surface gravity implies a radius that fits the orbit without filling the inner limit where matter would be stripped. Its chemical pattern is measured line by line with iron and alpha elements, offering a sketch of the gas cloud from which it formed. The preliminary picture leans toward a composition that is not rich in heavy elements, a trait that in turn whispers about the progenitor of the dark companion. A very massive star born from such gas would have weaker line-driven winds and would keep more of its mass until collapse. A collapse that is direct with little explosive fury would make only a small kick, and the binary would survive with its wide path more or less preserved. None of this is declared as a verdict. Each piece is offered as a clue in a chain that grows longer with every season of new measurements. The orbit keeps tracing its slow loop. The spectrograph keeps catching the star's breath. The two together keep saying the same thing in two languages at once, that gravity is heavy where no light is seen, and that the heaviest partners in the Milky Way may be the ones that prefer the dignity of silence. An orbit drawn in the dark begins as a set of patient constraints, each one rooted in a different way of watching the same star. The European Space Agency mission yields sideways motion on the sky, a slow ellipse that repeats with regular grace. Spectrographs on mountain tops yield the breathing along the line of sight, a careful rise and fall that follows the same calendar. When these records are braided, the orbit moves from suggestion to shape, and that shape presses on the mass that must be present though no light is seen. The period that the sky path suggests is checked by the rhythm of the radial velocities, and both agree that the dance takes years rather than months. The eccentricity that the sky path hints at is tested by the way the velocities climb faster near pericenter and linger near apocenter, and the test confirms a stretch that is real but not extreme. The inclination which turns a full three-dimensional loop into a flattened figure on the celestial sphere reveals itself in the ratio of the axes of the astrometric ellipse and in the amplitude of the velocity swing. The angle is not a trick or an artifact. It is a real tilt that lets the system tell its story with uncommon clarity. Once period eccentricity and inclination settle into a coherent solution, the center of mass emerges as more than a concept. The distance from parallax converts angles into physical reach. The size of the orbit is no longer a narrow line on a chart but a span in ordinary space, and the momentum shared between seen and unseen partners comes under arithmetic that is old and unyielding. A white dwarf cannot claim such momentum without adding light. A neutron star cannot supply the needed pull without signs that betray dense magnetism or bursts of captured matter. The mass that matches the motion belongs securely to a black hole. This conclusion grows firmer as every possibility that could counterfeit the orbit is pulled apart. Instrument effects are checked by splitting the data by season, by scan direction, and by detector configuration, and the ellipse survives intact. The photocenter could in theory be tugged by a faint star, whose light does not register separately, but deep images and clean colors rule out a second luminous source at the needed closeness and brightness. The spectral lines could be skewed by surface weather, yet the line shapes remain consistent once the orbital shifts are removed, and the brightness of the star does not wander as a spotted surface would make it do. The case does not rest on a single test, but on many that converge. The orbit that remains after this long winnowing carries its own personality. It is wide enough that tides never ground down the eccentricity into a near circle. It is long enough that the companion star ages on human timescales without change to the path that the partnership has kept for many cycles. It is tilted enough that a small error in angle cannot sweep the mass down into the realms of lesser remnants. The path suggests a system that survives because its birth was quiet. A giant star that collapses directly into a black hole without a violent explosion can keep a companion bound. A birth kick that is small or absent lets the original wide path remain wide, and a wide path deprives the black hole of the steady stream of matter that would otherwise blaze in high-energy light. The current silence in X-rays and radio then becomes not a surprise, but a signature of this history. The visible star adds more than a location and a velocity. It carries the parameters that control the orbit fit. Its temperature, luminosity, and surface gravity place it on a track of stellar evolution that sets its own mass within modest bounds. The measured distance rescales its brightness into an intrinsic light that matches that track, and so the visible mass becomes an anchor in the mass function. Without this anchor, the unseen mass would float across a wider range. With it, the inference tightens until the remaining interval leaves no room for a white dwarf or a neutron star. The companion's chemical pattern read through the strength of iron lines, and of alpha element lines leans toward a picture of formation in gas that does not overflow with heavy elements. That makes a quiet, heavy remnant easier to produce because winds that depend on metal lines are weaker when the surface holds fewer such lines. A massive star can then reach collapse with more of its original mass intact. The speculation does not outrun the data. It walks alongside them. It acknowledges that surface abundance can be altered by time, that mixing can blur the story, and that past exchange, if it happened, could paint over older memories. Even so, the companion star's chemistry fits a narrative in which the dark partner forms heavy and falls gently into its present state. The orbit solution thus acts as both measuring stick and detective. It measures the mass of the unseen partner through motion alone while it detects the fingerprints of a birth that avoided violence. It does not need a flare, a burst or a storm to argue for a black hole. It needs enough time, enough precision, and a star steady enough to carry the signal without confusion. The way the ellipse aligns on the sky, the way the velocities phase with the astrometric motion, and the refusal of the system to announce itself in other bands together, produce a kind of negative image, a silhouette whose edges are defined by absence as much as by presence. Into this image the name settles Gaia Bh3, an index in a growing catalogue of dark companions found not by spectacle, but by restraint. The label is not theatre, it is bookkeeping. Yet the bookkeeping rewrites expectations. Many believed that the galaxy's heavier stellar black holes would be the loud ones gorging on matter and lighting the sky in hard light. This orbit says otherwise. It says that the heaviest can be the quietest, that gravity alone can leave a trace deep enough to weigh, and that the census of such bodies must extend beyond the famous bright few. The orbit solution is not the end of the inquiry. It is a map for what to watch next. Continued astrometry will shave the error bars on inclination and eccentricity. Continued velocity work will hunt subtle departures from a perfect two-body model that could reveal additional distant companions or long-term drifts. Deeper searches in high-energy bands will set even tighter ceilings on any trickle of accretion. The star will continue to walk its curve, and each pass will give the black hole a more exact mass. With each refinement, the argument for a formation by direct collapse, for a natal kick that is small, and for a broad, steady orbit that starves the black hole of fuel becomes easier to believe. The orbit drawn in the dark is a quiet triumph of measurement, and it points ahead to a galaxy where many similar ellipses wait to be read. A name in a catalogue begins as an administrative act, the tidy business of turning a pattern in numbers into an entry that other researchers can find test and argue with. Yet the moment carries a quiet weight that spreads far beyond bookkeeping. The designation Gaia Bh3 threads through databases and summary tables into observatory schedules and proposal abstracts, and into lists that graduate students carry on clipboards and on laptops as they trace the latest objects that bend expectations. A label stabilizes the conversation. It allows papers to speak the same language even when the authors disagree about interpretation. It also carries a tacit promise that the evidence has passed a threshold, that the wobble on the sky and the breathing in the spectrum are not whims but persistent facts. In the lineage of catalogued dark companions, this one wears a distinction that is plain and startling at once. Among stellar mass black holes in the Milky Way identified by the quiet geometry of an orbit, rather than by the noise of accretion, it stands as the heaviest. The statement is careful in its bounds and therefore powerful. It does not claim to outmass every remnant in the galaxy, because the galaxy keeps secrets shrewdly. It claims to lead within the class that astrometry and radial velocity allow a class that grows with every cycle of data release and with every return to the telescope. The name makes the system legible, and legibility invites scrutiny. With a label, teams that were not present at the first discovery can bring fresh instruments and new habits of doubt. They can attempt independent reductions of the European Space Agency mission data test, different priors on the orbital fit, and ask whether the photocenter's dance could be reproduced with hidden light-blended neighbors or a Baroque model of stellar activity. They can return to the visible star with different spectrographs and extract velocities through different templates, checking for systematics that might have crept in through calibration telluric correction or template mismatch. They can draw on archives across wavelengths and set even sterner limits on any whisper of accretion. The label becomes an engine. It powers the cycle by which science tests itself against its own hopes. A catalogue entry also threads the object into memory. When planners think about how the next European Space Agency mission or the next ground array should distribute time, the presence of a heavy, silent black hole in an ordinary neighbourhood modifies the calculus. Surveys that once emphasized the violent and the transitory begin to balance their menus with programs that stare and wait, that harvest the slow physics of gravity as it plays out in wide eccentric partnerships. The existence of Gaia Bh3 makes it easier to argue that patience itself is an instrument that astrometry and quiet spectroscopy are not merely supporting tools but primary discovery engines for a population that has escaped attention by refusing to shine. The name also pries open imagination in a disciplined way. To call the object the heaviest within its detection class is to admit that mass sits at the center of the mystery. Heaviness without light pushes the field toward questions about formation that have simmered at the edge of models for years. If a very massive star can collapse directly without a theatrical explosion, leaving behind a heavy remnant and a wide, mostly unshaken orbit, then the Milky Way can grow a hidden backbone of dark weights that influence how spiral arms stir and how clusters relax. If the progenitor's surface held fewer heavy elements, the winds would have been weaker and the remnant heavier, and that possibility links this quiet system to the earliest epochs of star formation, when metals were scarce, and massive stars shed less of themselves before death. The name anchors these speculations to a specific case. It keeps theory honest by attaching conjecture to measured numbers. In a subtler sense, the catalogue entry grants the system a presence in the larger story of measurement. The European Space Agency mission was built to map the Milky Way with a cold eye, to turn positions and motions into a dynamic atlas of the disk bulge and halo. The discovery of a black hole by the curvature of a single star's path is not a detour from that mission, but an extension of it. The atlas does not only count stars, it also weighs what does not shine by how it makes stars move. By naming Gaia Black Hole 3, the catalogue folds the invisible into the map in a way that schoolroom atlases never could. The name then meets the world of follow-up. Observers put in requests to the European Southern Observatory, to other southern facilities, and to northern sites that can catch the star when it rises higher. They ask for additional seasons of radial velocity for high contrast imaging, to keep chasing the ghost of a second luminous partner, and for deep exposures in high-energy bands that might catch an outburst should the orbit carry the bright star a little closer one day. The requests cite the catalogue label, because the label unites their aims. It assures time allocation committees that the object is not a rumour. As the seasons pass, the name also becomes a marker for patients who read astronomy headlines in newspapers and on faint blue screens. They learn that black holes need not announce themselves with storms. They can be inferred by the most ordinary of motions, a star that does not walk straight. The public story thickens with the scientific one. The image of a monstrous whirlpool of light gives way to the steadier and perhaps deeper image of weight without shine. In that shift, the catalogue does cultural work as well as scientific work. A quiet entry loosens the hold of spectacle over what counts as discovery. Inside the field, the label exerts pressure on models. Groups that simulate binary evolution must now explain a heavy remnant in a wide eccentric orbit that shows no sign of a disruptive birth. They adjust mass loss prescriptions for massive stars at lower metallicity. They calm the natal kicks that once were assumed to be common. They explore pathways in which a companion survives the swelling and loss of the primary without being swallowed. They allow for the possibility that brief mass exchange might have altered the visible star's surface and then ceased leaving chemistry that is hard to pass. They confront the idea that a large share of stellar black holes may spend most of their long lives in silence, interacting only through gravity. The catalogue entry forces a reckoning with selection effects. The fact that the heaviest of its class appears in an ordinary neighbourhood asserts that the search so far has been shallow in one dimension and deep in another. It has been deep where sparks fly and shallow where the only sign is motion. With Gaia Black Hole 3 now sitting in the ledger, the balance begins to change. Proposals multiply to mine the European Space Agency pipeline for more such wobbles, to build automated alerts when a long-period ellipse crosses a threshold of significance, and to pair these alerts with spectroscopic campaigns that can compress the uncertainty on inclination and mass. Quiet systems that would once have been dismissed as routine become suspects. Giant surveys of spectra gathered for other reasons, including studies of exoplanets and stellar oscillations, gain a second life as black hole detectors when their time baselines happen to match an orbital beat. The name in this way is a lever. It wrenches open drawers that have been shut by habit. Yet even as the label spreads, the essential mystery remains intact, and that is part of its power. To call this object Gaia Black Hole 3 is to admit that knowledge can advance while a core stays dark. The mass can be weighed with narrowing error, the orbit can be drawn with growing elegance, the companion star can be typed with care, and still the central body refuses to present a surface or a spectrum. It holds to the one signature that no catalogue can domesticate: the steady insistence of gravity. The more times the name is spoken, the more the field is reminded that not all discovery glitters. Some discoveries deepen the night by showing how rich its quiet can be. The visible companion at the heart of this quiet orbit carries a face that seems older than its neighbours, and that impression begins with temperature and light. Its spectrum, taken across many seasons and cleaned until only the star remains, places it in the calm middle grounds between hot blue youth and cool red senescence. It glows with the steady warmth of a star that has burned long enough to settle into a rhythm, yet not so long that its outer layers have swollen into a fragile shell. When the measured distance scales its brightness into an intrinsic light, the point lands on the familiar diagram that relates colour to absolute magnitude, in a place that suggests mild evolution from the long plateau of hydrogen burning. Surface gravity read from the subtle pressure broadening of lines supports the same picture, not a puffed giant, not a compact dwarf, but a star that has begun to unspool the balance it held for so long. Rotation adds a quieter note of age. The absorption lines are narrow without being knife-thin, a sign that the surface does not spin with the headlong speed of youth. The projected rotation extracted by matching the shapes of many lines together hints at a body that has slowed with time and with internal rearrangement, a star that spins in measures rather than in rushes. Such calmer rotation blesses the radial velocity measurements by keeping the line cores sharp, but it also becomes a clue in its own right, a whisper that the companion is not a fledgling, but a creature of many stellar seasons. Chemistry then opens the door to a deeper dissonance with the surrounding neighbourhood. The lines of iron measured against nearby lines from elements formed in different chain reactions suggest a surface that holds fewer heavy elements than the average for stars in the local galactic disk. The pattern is not a blanket deficiency. Some of the so-called alpha elements forged in the rapid furies of massive stellar deaths appear less depleted relative to iron, a trait that often points to birth from gas enriched by early generations of giant stars rather than by the slow yield of smaller ones. The ratio of these elements is read not from any single feature, but from the chorus of many lines across the optical range, each corrected for the small effects of temperature and gravity, each weighted by its reliability. The result is not a startling outlier, but a steady lean toward lower metallicity, a lean that carries consequences. Stars with fewer heavy elements shed weaker winds during their lives, because the lines that absorb and push the outer layers outward are fewer and less effective. A very massive progenitor born from such gas would have lost less mass before collapse, and that path would help produce a heavier remnant. The visible star wears this story on its surface like a faint watermark, a record of a birth cloud that was not rich in complex elements. Yet surfaces can lie, or at least they can blur the truth. Mixing in the outer layers can dredge up products of nuclear burning that alter the strengths of certain lines. Past mass exchange, if it occurred when the now dark partner was still evolving, could have dusted the companion's surface with processed material and confused simple readings. The current orbit is wide enough that ongoing exchange is unlikely, but history may contain brief directional events that left imprints. The analysis, therefore, walks carefully, treating the chemistry as a strong clue rather than an unshakable verdict. In concert with chemistry, the star's motion through the galaxy adds another brushstroke. Proper motion and radial velocity together sketch a spatial velocity that is calm by the standards of halo wanderers, yet somewhat more energetic than the youngest thin disk population. The path may lift gently above and below the galactic plane, a trait that hints at a mixed lineage between the smoother thin disk and the thicker older component that remembers earlier times. None of these indicators demand an exotic origin, but together they tilt the scene toward an ancestry that is older and leaner than the immediate surroundings. The star thus appears as a modest elder among younger cousins, an emissary from a chapter when the Milky Way's gas carried fewer heavy atoms. Its atmosphere reflects thinner winds in its birth generation, and through those winds it points to a progenitor that could fall into a heavy black hole with little fuss. Temperature and luminosity now step back into the spotlight this time as inputs to the mass of the visible star itself. Stellar evolution models matched to the measured composition map the observed brightness and colour to a narrow allowed mass. That visible mass is a fulcrum in the mass function derived from the orbit. Shift it upward, and the unseen partner must grow even heavier to keep the centre of mass where the motion demands. Shift it downward, and the unseen partner shrinks but only within limits allowed by the velocities and the tilt. The measured temperature, the cleaned parallax, and the surface gravity conspire to keep the visible mass in a corridor that refuses to rescue the unseen object from the heaviness that the orbit requires. The result is robust to the kinds of small systematic errors that can haunt such work. Changes to the adopted interstellar extinction within reasonable bounds barely move the point on the diagram. Different calibrations of the temperature scale shift the atmosphere by less than the width of the corridor. Varied microturbulence and slight choices in the line list nudge the chemistry but do not rewrite it. Each of these checks matters because the story the companion star tells carries implications that reach far beyond one system. If heavy black holes prefer partners that look like this, then surveys can be tuned to favour such candidates. If the key is lower metallicity coupled to a wide orbit, then parts of the sky with older populations become richer hunting grounds. If slow rotation and steady light are common among such companions, then high cadence photometry that often flags stellar agitation can act as a filter rather than a target list. The companion star therefore moves from subject to guide, from a character in one binary to a template for a hidden population. In a final twist of quiet irony, the star that acts older may not be substantially older in absolute years than many of its neighbours. It may simply come from a stream of gas that by the luck of galactic mixing carried fewer heavy elements into its nursery, even at a relatively recent time. The Milky Way is not a neat layer cake. It is a stirred ocean where pockets of different composition can persist and give rise to families with slightly different destinies. The companion's measured traits lean toward that more tangled picture, and in that tangle the path to a heavy silent black hole becomes not only possible but natural. The star's surface, with its calm rotation and lean chemistry, records the memory of winds that were weaker and of a partnership that survived without a violent beginning. It stands now as a witness that shines while its partner refuses to, and everything it says in light confirms that the heaviest part of this system is the part that chooses darkness and leaves gravity to speak. Metal and memory meet in the thin lines that stitch the star's spectrum together, because chemistry is a biography written in quiet ink. The visible companion surface carries a pattern of elements that does not exactly match the neighbourhood average, and that mismatch becomes a lens through which the dark partner's past is watched more clearly. Analysts begin with the anchors measuring iron against hydrogen to sketch an overall metallicity. Then they look to the so-called alpha group elements like oxygen, magnesium, silicon, calcium, and titanium that are forged in the explosive ends of very massive stars. The companion shows a mild elevation of these alpha elements relative to iron, not a shout, but a measured lean, and that lean is significant because it implies that the gas from which the star formed was enriched more by short-lived giants than by the longer-lived smaller stars whose deaths produce more iron. From there the portrait becomes finer. Carbon and nitrogen lines hint at gentle mixing in the star's outer layers, enough to nudge the balance without rewriting it. Lithium, fragile in stellar envelopes, is depleted as expected. For a body that has aged beyond early youth, a small check that sits comfortably with the temperature and surface gravity already measured. Barium and strontium, which can trace the slow neutron capture process inside older giants, are not wildly enhanced, suggesting that the companion has not been heavily dusted by material from an ancient neighbour that once swelled and then faded. europium more tightly linked to the rapid neutron capture process thought to occur in some violent stellar deaths, does not stand far above iron, so there is no strong flag of rare enrichment. These small absences matter. They argue against a history in which an asymptotic giant companion poured processed material onto the surface and masked the original birth mix. What remains feels closer to an untouched record of the natal cloud. The record says the cloud was lean in heavy elements compared to many local stars, and that leanness draws a line back to a time or a place in the Milky Way where chemical enrichment had not yet run to completion. The star's atmospheric parameters then serve as a scaffold on which ages can be estimated. Isochrones, the curves in the diagram that relates colour to absolute magnitude, that gather stars of the same age and different mass, are matched to the observed temperature and brightness given the measured metallicity. The age that falls out is not extreme older than the youngest thin disk, but not as old as the thick disk or halo elders. In parallel, asteroseismic hints, if present in archival time series, could refine this age by reading the scale of the star's global vibrations, though the data may be too sparse for a firm reading. Gyrochronology, the method that ties rotation to age for certain classes of stars, plays only a supporting role here, because the rotation is steady, but not precisely measured enough to be a clock on its own. Even so, all roads converge on a middle age that fits a birth in a slightly older pocket of the disk or in a stream of gas that carried memories of earlier epochs. Kinematics offers a second independent glimpse. Proper motion and radial velocity join to define a full space motion that is modestly warm with a vertical bob above and below the plane that is larger than the youngest populations but quieter than the ancient halo. The orbital path through the galactic potential, reconstructed from this motion, suggests a life that stays within the broader disk while sampling regions of slightly different metallicity. None of this forces an exotic migration. It simply means that the star may have formed in a cell of the galactic gas, where heavy elements were fewer either because the local rate of star formation had paused, or because fresh, more pristine gas had flowed in and diluted the mix. Against this backdrop, the heaviness of the black hole becomes more natural. Lower metallicity progenitors lose less mass to winds, and thus more mass can fall inward at the end. A direct collapse without a loud explosion would leave the orbit wide and eccentric as observed with a small or absent birth kick, allowing the binary to survive. The companion's chemistry thus whispers that the pathway to a heavy silent remnant did not require a violent reshaping of the pair. It required the quiet arithmetic of weaker winds and a calm fall. Yet the same chemistry leaves puzzles scattered like faint footprints. Some ratios sit in between the classic patterns of thin and thick disk stars, as if the companion belongs to a transitional family. The alpha elements are raised but not dramatically. The iron group elements align with a moderate metallicity deficit but show small deviations that could be the echo of subtle mixing. Carbon sits a touch low relative to oxygen, which may reflect internal processing or a birth cloud skewed by the yields of a few nearby giants. These tensions do not overthrow the story, they enrich it. They hint that the birth environment may have been a meeting place of gas parcels with slightly different pasts. The prospect of past mass exchange cannot be dismissed entirely. A brief phase when the progenitor of the black hole swelled could have draped the companion's surface with processed ashes before the collapse. If so, the lack of strong barium and strontium enhancement suggests that the exchange did not come from the slow neutron capture interior of a long-lived giant, but from layers where carbon and nitrogen walked a narrower line. In that case, the chemical portrait becomes a layered image, part memory of birth, part memory of a short directional wind. Disentangling these layers will require deeper spectra extension into the near-infrared, where different lines carry different sensitivities, and perhaps the leverage of polarimetry to test for scattered light that would betray subtle circumstellar matter. Meanwhile, the chemistry already on the page reframes selection strategies. If heavy, quiet black holes often accompany stars with mild alpha enhancement, and slightly lower iron surveys can seek such spectral fingerprints among bright field stars that show astrometric hints of a wobble. If lithium is routinely low and rotation is moderate, these variables can join machine learning filters that comb large spectroscopic archives for promising targets. The companion's elements thus become not only memory but map guiding where to look for cousins. In the larger galactic picture, the existence of a heavy silent remnant in a system whose companion bears the marks of leaner gas links, present-day neighborhoods to earlier chemical regimes. It suggests that the galactic disk carries within it a fossil record of dark remnants that were seeded by stars born when metals were fewer and winds were gentler. The census of such bodies will change estimates of the mass that dark stellar corpses contribute to the disk, altering how models of spiral arm dynamics and disk heating are tuned. It will also press theory to accept that the black hole mass function in the Milky Way is not defined only by the loudest sources, but by the quiet majority that leaves chemistry and motion as the only clues. In that sense, metal and memory do more than decorate a case study. They lift a local story into a galactic one where the heaviest actors move unseen, while their partners carry the handwriting that tells where and how such gravity came to be. Silence from the accretor feels at first like an absence, but in this system, it becomes a firm presence that shapes each conclusion, because the invisible partner remains dark across bands where hungry black holes shout. The wide and mildly stretched orbit gives room for stillness. The bright star does not fill its critical boundary, where matter would spill steadily and its wind drifts outward, with the soft push expected for a star of its temperature and surface gravity. In such a regime, only a small fraction of the outflow can be captured by the compact partner, and even that trickle is starved by speed and distance when the path carries the stars far apart. The result is a rate of inflow so slight that it may never build the hot boundary and dense inner spiral that produce hard light. Space telescopes that listen for X-rays have stared and have found no spark at the measured position, even when the orbit was near its closer bend, and radio arrays that can hear a small jet or a weak outflow have also found no sustained whisper above the noise. This silence does not refuse physics. It spells out physics of scarcity in which gravity gathers less than the flow can cool and shine. The black hole therefore lives in a mode that astronomers call quiescent, a word that hides within it many specific conditions. The gas that drifts inward from the wind arrives tenuous and warm, and shocks that might heat it further peter out across large distances. Without a reservoir, the inner region can become advection-dominated, carrying heat inward rather than glowing efficiently, and what little light leaks out may be too faint to register against the night. The absence of a luminous disk also removes the strong ultraviolet and X-ray flux that would sculpt the companion's atmosphere, so the spectrum of the bright star stays clean without the extra emission in hydrogen lines that marks active accretion. This calm agrees with the steady photometry and with the narrow, well-behaved absorption lines that allow precise velocity work. The orbit's slow heartbeat sets the stage for occasional questions about fleeting outbursts, because some binaries that usually starve will still flare when a patch of wind grows denser, or when a mild tide focuses the flow near closest approach. Here, repeated checks across the cycle show no flash, not even a brief rise that would betray a gulp. That record constrains both the geometry of any weak disk and the character of the wind. the wind must be clumpy only in moderation, or else its knots do not reach the compact partner. The disk, if it exists at all, must be faint, cool, and perhaps truncated far from the last stable orbits where gravity would turn matter into hard light. A different class of explanation invites caution, and then recedes. Some remnants can spin down magnetized inflow and throw it back out, a kind of propeller effect, but that mechanism depends on a firm magnetic field and a hard surface, neither of which a black hole can supply. Another idea asks whether dust or gas along the line of sight veils a low flicker of high-energy light. Yet the measured colours of the star and the clarity of the spectrum argue that the view is not heavily dimmed, and the limits from multiple bands agree with one another. In the end, the simplest reading remains: the system is quiet because it is wide, and the black hole is heavy because it formed without a blast that would have broken the partnership and driven the path into chaos. Silence from accretion then becomes a powerful selector, because it implies that heavy black holes discovered by the gentle pull on a star will not offer watchdogs in other bands to confirm them, and therefore the full case must rest on geometry and on careful patrols that find nothing where a different model would predict something. This shifts how surveys think about completeness. Catalogues built from flares and bursts carry a bias toward tight orbits, strong tides and thick disks. They overlook the giants that move the most mass through gravity and the least through radiation. The current system stands as a counterweight. It says that some of the most massive stellar remnants survive by doing almost nothing that can be seen, and that the Milky Way may hold many such bodies in plain sight, each tucked into a long, steady partnership that starves it of fuel. The lack of high-energy light also protects the companion's surface as a fossil record. Without a strong bath of hard photons or a persistent stream of incoming particles, the atmosphere is not stripped ionized or driven into flares. Element lines retain their quiet shapes, so chemical ratios can be trusted as reflections of birth and slow evolution, rather than as scars of ongoing assault. That in turn makes the companion a more reliable witness about when and where the pair formed, and strengthens the link between lower metallicity gas and a path to a heavier remnant. At the same time, silence hints at how these dark partners may influence the larger disk. A heavy body that does not flare can still tug clusters, thicken the thin layer of stars and rattle streams that pass nearby. It can alter the small-scale texture of galactic motion without ever announcing itself with light or heat. If many such bodies hide among ordinary stars, their gravity becomes a background percussion that can warm the disk over billions of years. The only way to count that percussion is to listen through astrometry and through long lines of radial velocity, because those are the methods that do not ask for a glow. The case study here demonstrates the program. The astrometric ellipse and the spectral breathing tell the entire story that a mission would have told, with the added benefit that they weigh the culprit directly, rather than through models of messy flows. Continued observations will sharpen both the orbit and the silence. Tighter limits in X-rays and in radio will compress the allowed room for any weak disk, while continued calm will turn a hint into a rule. Each season that passes without a flare will reduce the chance that hidden matter sits ready to feed, and each pass along the orbit that yields the same clean velocities will harden the mass of the unseen partner. Silence will keep acting as a measurement. In a broader sense, the absence of accretion becomes a philosophical pivot for the field, though the tone remains sober. It reminds researchers that the cosmos hides its largest local weights not behind fire, but behind patience. It says that surveys designed to stare and to time will find new classes of objects that surveys designed to catch sudden light will miss. It nudges plans for the next decade towards satellites that measure positions even more finely, toward ground arrays that can measure velocities with even calmer precision, and toward quiet multi-wavelength watches that confirm the dark by the persistence of nothing. The quiet is not empty. It is structured by gravity and by the chemistry of a wind, by the width of an orbit and the age of a star. It is the trace of a birth that did not explode and of a life that refuses drama. In that restraint, the system reveals how a heavy black hole can be present influential and yet almost perfectly mute, and how the Milky Way can carry a population of such mutes that will only be counted by listening to the softest motions of the brightest partners they never disturb. Kick or no kick becomes the hinge on which the system's path swings, because the orbit that exists today is the fossil of a birth that either jolted the pair or let it pass quietly through a dangerous moment. When a massive star dies, a violent explosion can throw off a large share of its mass, and can push the newborn remnant with a shove that astronomers call a natal kick. That shove can tilt the orbit, swell its shape into a more stretched ellipse, or tear the partnership apart entirely if the jolt and the sudden loss of weight are strong enough. A quieter pathway exists in which the star collapses almost directly into a black hole, losing little mass to a blast, and sending little to no impulse through the shared orbit. The present system, with its wide path, real but moderate eccentricity and sustained bond, speaks more easily in the language of the second pathway. The long period tells that tides have not been strong, so the current eccentricity is likely close to what the system carried after the collapse, with only slow changes since. The tilt of the orbit, read from the ratio of axes in the astrometric ellipse and from the amplitude of radial velocities, is consistent with a geometry that does not demand a chaotic twist. The distance and proper motion allow the space velocity of the pair to be placed within the context of the local galactic flow, and the star does not race through space as a survivor of a blast might. Its motion is warm rather than wild, its vertical bounce above and below the plane present, but not extreme, and those facts together make a strong case that the collapse sent little shock into the system. The chemistry of the companion leaning toward fewer heavy elements supports this story in a second way, by favouring a progenitor with weaker winds. With less mass lost during life, the star that collapsed could hold on to more of itself until the end, and a final fall that was closer to direct would remove less mass and impart a smaller gravitational tug on the orbit in the instant of death. The classical scenario in which half or more of the system's mass is ejected in a few heartbeats would have widened the orbit more drastically often to the point of dissolution, or would have left the pair bound, but with a high eccentricity that tides could not erase at such a wide separation. The measured eccentricity is not small, yet it is gentle compared to what a violent blast would commonly leave behind. It can be read as a trace of a mild impulse, or as a relic of prior binary evolution that never felt strong tides. In either reading, the numbers prefer a small or absent kick. The velocity curve of the visible star adds another layer of constraint. The phase of its fastest approach and fastest retreat relative to the astrometric ellipse helps fix how the orbit sits in space. When a large natal kick bends the plane or flips the argument of pericenter, the resulting geometry tends to reveal itself through mismatches that require contortions in the model. No such contortions are needed here. The solutions that best fit the data are those in which the orbit looks like a scaled-up version of what it likely was before collapse, altered mainly by a modest change in total mass rather than by a shove. There are other quiet fingerprints. The system lacks the misalignments between the spin of the companion star and the orbit that often follow a large impulse, at least within the limits of current measurement. Measuring such misalignment directly is hard without transits or detailed astroseismology, but the narrowness and symmetry of the absorption lines combined with the calm rotation leave little room for a dramatic tilt that would show up through strange gravity darkening or through long-term nodding of the orbital plane. The absence of these signs does not prove perfect alignment, yet it narrows the range of kick strengths that would remain plausible. The simplest picture grows clearer. A very massive star formed from gas with fewer heavy elements, kept much of its mass through life, and then fell into a black hole with little explosive show. The binary stayed bound, retaining a wide path and a modest stretch. The newborn black hole did not receive a sharp push, so the centre of mass of the pair did not lurch. That history explains why the system moves through the Milky Way like an ordinary member of the disk, rather than like a scarred refugee. It explains why the present separation leaves the compact partner hungry and dim. It even fits with the lack of circumstellar debris that would have followed a blast, because deep images and spectra do not find leftover shells or odd absorption that would mark a recent violent shedding. A small set of caveats keeps the mind honest. A kick could have been delivered, but in a direction that largely cancelled the widening from mass loss, leaving a lucky orbit that mimics a quiet birth. Such fine-tuning is possible, but grows less likely as the number of needed coincidences grows. A brief phase of non-conservative mass transfer before collapse could have adjusted the eccentricity, but the wide orbit today suggests that any such phase was restrained. A slow neutral wind from the progenitor might have left a faint cold cloud that current searches would miss, but that cloud would influence the companion's light through reddening, and the measured colours do not require unusual dust. Each caveat, when chased, drifts toward more complexity than the data demand. The gravitational census that Gaia and the spectrographs together provide is therefore not only a measure of mass, but a record of quietness. That quietness carries a profound implication for the unseen population. If heavy black holes often form by direct collapse with small kicks, then wide binaries with old or mildly lean companions become preferred harbours. Many will be too wide or too slightly stirred to reveal themselves even to Gaia. Some will fall below thresholds or will masquerade as mild noise in the astrometric residuals. Others will reveal themselves only after many years of patient measurement. The lesson is twofold. First, the number of heavy black holes in the disk may be higher than models tuned on loud sources predict. Second, the spatial distribution of black hole remnants may reflect the smoother flow of the disk rather than the hot high-velocity tails that large kicks would inject. Disk heating, spiral arm stirring, and the long-term survival of clusters all respond to this hidden mass. The nature of the kick therefore writes itself into the choreography of the Milky Way. To settle the matter further, researchers will press for even tighter orbits, for even more precise proper motions, and for long baseline velocity curves that catch any slow drift from distant companions. They will look for subtle variations in the companion's line shapes that could betray precession or a mild misalignment. They will compare the space motion of this system to simulations of binary populations under different kick prescriptions. Each added bit of restraint will favour or disfavour a quiet birth. The present balance leans towards stillness. It offers a view in which the heavier stellar black holes of the disk are born not with a bang but with a fall, and the orbits that cradle them keep that memory in shapes that are stretched but not torn wide but still bound, old enough to be stable and quiet enough that only gravity gives them away. Ghosts in plain sight become the natural extension of a discovery that depends on patience rather than spectacle, because a heavy black hole that hides inside a bright star's motions hints at a crowd of cousins that survey pipelines have not yet learned to notice. The Milky Way is an ocean of binaries spread across the disk, the bulge and the lower halo, and many of those pairs are wide enough that tides do not bite and winds do not feed. In such pairings, the compact object can be massive and yet stay almost perfectly dark, exerting its influence only through the slow choreography of gravity. Gaia black hole. 3, by virtue of weight without light, converts that idea from a theoretical possibility into an observational mandate. If one heavy remnant sits quietly beside a bright companion, then similar systems likely inhabit many long ellipses that pass as ordinary until their subtle deviations are added up. These ghosts escape the habits of attention that have defined the field for decades. X-ray monitors prefer transient fireworks. Radio surveys catch jets and winds. Optical flares grab time on telescopes that are built to race after explosions. Wide quiescent binaries do none of these things. They require stable imaging that repeats over years, and they ask for spectrographs that trade drama for consistency. The practical effect is that the known catalogue of stellar black holes has been built from a biased sample favouring the hungry and the close. The quiet, the wide and the heavy find themselves undercounted. Gaia changes that ledger by turning absence of light into a measurable presence of motion. The path from a hint to a census then runs through selection effects that must be made explicit. Astrometric sensitivity scales with brightness distance, and the size of the wobble projected onto the sky. Nearby bright stars carry photocenters that can be measured to the smallest steps, while fainter or more distant targets blur into noise where the same wobble would go unseen. The inclination of the orbit also matters, and so does the share of the orbit covered by observations. Long periods can be hard to confine if the mission samples only a fraction of a cycle, and very short periods can wash out if the ellipse projects poorly. Radial velocity follow-up introduces further filters because stable lines moderate rotation and steady atmospheres make the work clean, while restless surfaces complicate the cross-matching of templates. Each of these filters prunes the tree in a direction that is not randomly aligned with the underlying population. Heavy black holes in very wide orbits move their partners more, but they also often live with companions whose lines are broad or whose brightness saturates delicate instruments. Some will be in crowded fields where blends counterfeit or erase small shifts. Others will share their light with a faint third body on a very long path that perturbs the velocities by a slow drift, confusing simple two-body fits. To find ghosts in plain sight, the field must not only measure more precisely, it must learn to see around its own blind corners. That learning takes the form of careful forward modelling. Researchers generate synthetic Milky Way neighbourhoods populated with binaries whose birth masses, separations, eccentricities and metallicities draw from distributions tuned by star formation histories. They evolve those virtual populations under different prescriptions for stellar winds, for mass exchange and for the manner of collapse. Some versions grant large natal kicks, others keep collapse quiet. They then pass these virtual catalogues through the selection pipelines of astrometry and spectroscopy, including the actual scanning law of the spacecraft and the noise properties of real instruments. The fraction of artificial ghosts that the pipeline would have recovered becomes a function of period distance, mass, and brightness. Against that function, the detection of a heavy quiet system like Gaia Bh3 calibrates the model. If the model says such a system is very unlikely to be found given the selection, yet it was found early, then the underlying population must be larger than initially assumed. If the model says such systems are easier to detect than thought, then their scarcity in the sample would argue that the heavy tail is thin. Either way, the presence of a named object pries open prior expectations and forces a rebalancing. A parallel route amplifies the signal by looking for families of signs rather than single flags. An astrometric ellipse of modest size, a radial velocity curve of small to medium amplitude, a companion with slightly lower metallicity and calm rotation, and a sky position in regions of the disk where older stars are more common together raise the chance that a system hosts a heavy dark partner. Machine learning tools can digest hundreds of thousands of stars and weight these features in ways that are transparent enough to test and adjust. The approach does not replace the measurements. It triages them, sending the strongest candidates to spectrographs and reserving time where it will tighten the most uncertain parameters. Microlensing surveys add a cross-check in different corners of parameter space. A dark lens that passes in front of a field star can magnify its light for days to months, and if the lens is isolated or in a very wide binary, the lack of light from the lens makes the curve clean. A few such events point to dark masses in the stellar regime. The union of astrometry velocity and lensing will trap ghosts that would otherwise keep walking. The inventory that results will alter familiar budgets. The number of heavy stellar remnants in the disk will rise, and with it the thin layer of mass that warms the orbits of sun-like stars. Spiral arms that pass near heavy invisible partners will stir stars a little harder. Star clusters that carry an unseen core of black holes will evaporate faster. The rate at which quiet binaries can be driven by mundane encounters into closer paths, and thus into eventual gravitational wave sources, will need to be revised because the raw material for such pathways will be more plentiful. Even the interpretation of future gravitational wave detections will change, since the mass spectrum of black hole mergers in the Milky Way's thickened halo may reflect a history seeded by binaries born quiet and later hardened by dynamical tides, rather than only by isolated field evolution. Ghosts in plain sight also recast the culture of observation. Programs once framed as housekeeping become discovery engines. Long baselines begin to sound like explorations rather than chores. The idea that patience can be as productive as speed finds a concrete footing in proposals. Teams that maintain immaculate radial velocity archives for exoplanet studies learn that their data harbors dark binaries as a second harvest. Teams that refine the astrometric calibrations take pride in the ghosts they have made visible by pushing down systematic errors another small step. The narrative that emerges is less about rare fireworks and more about common gravity at scale. It does not ask the sky to scream, it asks the sky to keep time. The heavy remnant that started this turn of thinking remains silent, but its presence moves thought outward. The galaxy becomes a stage where the largest local weights are carried by partners that look like dozens of ordinary field stars lying within a handful of hundreds of parsecs, and what separates them is not brightness, but the shape of a path drawn slowly enough to be seen. In that recognition stands the seed of a new census. It will not be complete soon. It will never be complete in any final sense. It will, however, be fuller with each passing year, and with each year the ghosts will step a little more firmly into view, still dark, still quiet, but no longer invisible to an eye that has learned to count by motion rather than by light. A map with blind spots is still a map, yet wise travellers trace its empty patches with as much care as its known roads, and the census of dark companions that rises from astrometry and radial velocity is no different. The European Space Agency mission draws a grand atlas of motion, but the atlas carries seams and stitches that change how easily an unseen partner can be found. The scanning law, the deliberate pattern with which the spacecraft sweeps the sky, gives some regions more frequent visits and others fewer, so the cadence of points in time is uneven. Orbits that whisper their presence through changes that align with dense clusters of visits will reveal themselves more quickly, while those whose key phases fall in sparser seasons will demand patience, or will be misread as straight lines plus noise. The measurement of the photocenter is itself shaped by brightness. Very bright stars can push detectors near their limits, inviting subtle non-linearities that require careful correction, while faint stars spread their light thinly enough that the smallest shivers vanish into counting statistics. Crowding changes matters again. In dense fields along the galactic plane and toward the bulge, the point spread functions of neighbours mingle, and even the most careful modelling can inherit slight shifts that mimic or mask a wobble. Variable stars introduce their own confusion, because photospheric changes can slide the effective centre of light even when the centre of mass does not move the same way. The catalogue fights these problems with models that learn from the whole sky, but learning does not erase limits. It makes them explicit. Even when the astrometric ellipse is clean, the tilt of the orbit can blunt the signal. A near face on view compresses the sideways motion, leaving only a small circle on the sky that requires high precision and long coverage to distinguish from slow instrumental drifts. A near edge on view exaggerates the ellipse, but makes the conversion from angle to mass depend more strongly on the radial velocity amplitude, and that amplitude depends on both the true mass and the tilt. Errors in tilt therefore feed directly into errors in mass, which means that the very cases that would be easiest to see in angles can be the ones most sensitive to spectrographic honesty. The spectrographs carry their own blind spots. Broad lines from rapid rotation smear the crossmatch used to extract velocities, especially for early-type stars where the rich thicket of metal lines thins. Pulsations, granulation, and magnetic activity can shift line centroids by small amounts that masquerade as orbital motion if their timescales imitate the cadence of observations. Telluric lines from Earth's atmosphere wander across the stellar spectrum as seasons change, and although they are modelled and removed, their ghost can still bias the slowest drifts. Long periods extend beyond human attention spans, so the velocity curve may show only a gentle arc rather than a full cycle, and an arc can be fitted by more than one story. A distant third body on an even longer path can add a slow drift that shifts the baseline and confuses the two-body solution. Each of these small unkindnesses is manageable in isolation. Together they compose a terrain in which some valleys of parameter space are easy to survey, while others hide objects that look only slightly less ordinary than the median field star. The catalogue of known systems therefore reflects not only what the sky holds, but what the instruments and methods prefer. Recognizing this preference opens the door to strategies that turn blind spots into targets. One strategy is to expand the time base relentlessly. A wobble that is borderline in the third release of data can become unambiguous in the fourth or the fifth, because the ellipse will have been traced more completely, and the annual parallax and linear proper motion will have been modelled away more strongly. Another is to focus radial velocity campaigns on classes of stars whose lines offer strong leverage even if they are less common. Bright, slowly rotating subgents with quiet atmospheres can serve as precision anchors. When a promising astrometric signal appears around such a star, the velocity curve can be drawn with fewer nights and with smaller residuals, which in turn reduces the need to assume strong priors on inclination. High contrast imaging adds a further layer by ruling out faint luminous companions that would bias the photocenter. Even a non-detection at small separations tightens the mass inference for the dark body by removing plausible light that would otherwise be folded into the fit. The blind spots of crowded fields can be pried open by combining catalogues. Where the European Space Agency measurements struggle in the brightest stellar swathes, ground-based surveys with different systematics can cross-check for blends. Adaptive optics images can separate near neighbours to feed cleaner inputs back into the astrometric solution. Photometric behaviour monitored by planet-hunting missions can flag variability that would otherwise masquerade as centroid shifts. None of these supplements replace the core methods. They clean the stage so that the quiet motion stands alone. A different form of blindness arises from human attention. Pipelines are built to reject outliers that do not match the expected error models, and in early work those outliers may include systems with truly unusual orbits. As experience grows, the filters can be retuned to catch long-period ellipses with small amplitudes without admitting spurious detections. Machine learning tools can be trained not only on positive examples, but on carefully constructed false cases to sharpen their judgment. Moreover, selection functions must be published with the same transparency as the catalogues, because only with a clear record of what was likely to be found can the absence of detections be interpreted. The map is then more than a list. It is a measured window onto a true population. A final family of blind spots lies in theory itself. Population models often start with assumptions about how often massive stars share wide orbits, how frequently metallicity leans low in certain neighborhoods, and how likely direct collapse is compared to explosive ends. These assumptions guide where observers look, which in turn feeds back into the models. A discovery like Gaia Bh3 forces a reweighting. If the heaviest, quietest binaries are easier to find than theory predicted, then the true number must be larger or their distribution different. If they are harder to find, then the fact that one was found near the Sun argues for an even higher underlying count. Either way, the blind spot is reduced as models and data chase each other into closer agreement. The next generation of missions promises to peel back more of the sky. A successor with finer astrometric precision would turn tiny circles into firm ellipses and would extend the reach to fainter stars and to more distant districts of the disk. A network of stable spectrographs scheduled with an eye toward long baselines would fill in velocity curves that now show only arcs. Radio and X-ray observatories standing by during pericenter seasons could put even stricter ceilings on any faint accretion, making silence a quantified constraint rather than a qualitative description. In all of this, the humility of the map must be kept. It is acceptable to admit where the sky remains dark to current tools, because that admission is the starting line for new designs. The atlas is already richer because gravity has been allowed to speak without light. It will grow richer still when the scanned seams are crossed. The crowded lanes are teased apart and the cadence gaps are filled, and in that future the heaviest quiet bodies of the Milky Way will step out of the blind patches into the measured light of motion one ellipse at a time, until the map is not complete, but undeniably less incomplete than it was. Clues in the long period arrive slowly, but they arrive with a steadiness that withstands fashion and favours patience. The orbit that carries the companion star around the dark mass takes years to complete an interval that would frustrate a survey built to chase sudden light, but that rewards those who prefer to watch a curve mature. A long period means wide separation for most of the path, and wide separation means that tides nibble rather than bite. The star keeps its shape, the atmosphere stays calm, and the surface retains the memory of birth more faithfully than in cramped binaries where gravity rubs away the past. The measured eccentricity, neither a near circle nor a wild stretch, preserves that memory with subtlety. It lets the pair linger at the far point where motion is slow, the better, to take careful spectra and lock down velocities with minimal blurring, and it carries the star inward to a closer pass where the difference between apocenter and pericenter acts as a test of the orbit model. The ratio of velocities near these extremes of distance grows into a check that does not rely on light from the accretor at all. Year after year, the points fall where the predicted ellipse says they should, and the absence of a flare during closer approach connects geometry to quiet physics. In some binaries, even a long period cannot shield the companion from brief feeds of matter, when tides concentrate a wind near pericenter and sudden brightening follows. Here the continued stillness near the closer bend argues that the wind is thin and that the capture radius of the black hole is small compared to the scale over which the wind disperses. The long period thus translates into a physical picture of a black hole that crosses streams too diffuse to drink. The length of the orbit also constrains the birth that preceded it. If the collapse that formed the black hole had thrown a strong kick, or had removed a large fraction of the system's mass, very suddenly the orbit would likely have inflated much more, or would have broken. Instead, a moderate eccentricity joined to a wide path looks like a partnership that survived with its shape approximately preserved. The long time scale has then allowed that shape to relax only slightly, because weak tides cannot quickly turn a stretched track into a circle. The present eccentricity is therefore a relic, a fossil curve held for many cycles, and so the degree to which it departs from a circle becomes a ruler that measures the violence of the past. In this system, the ruler points to restraint. The length of the period serves as a switch that turns off many confusing effects. In shorter period binaries, the companion star may show tides that pull its figure out of round rotation, lock to the orbit that smears lines into broad bands, and magnetic activity fired by complex interactions with a hot bright disk. Long-period systems sidestep these confounders. The companion here rotates at a pace set by its own history rather than by tides, so the absorption lines remain narrow enough for precise velocities. The photosphere is not hammered by hard light from a nearby accretion flow, so the chemistry visible at the surface is closer to original. Even the shape of the line cores remains steady across the seasons, with no evidence for pulsations driven by tidal forcing. Each of these absences is a gift from the long period. They simplify the route by which the mass of the unseen object is inferred. They reduce the number of ways that the data can be tricked. The timescale also lines up with the goals of astrometry. A mission that watches for many years can catch enough of a slow ellipse to discriminate it from a straight drift plus noise. The long period allows the peculiar speed profile of an eccentric orbit to be traced a fast sweep near the close approach, a contemplative dawdle near the far point. This asymmetry is hard to counterfeit with instrument errors that do not know the calendar of pericenter and apocenter. In the present case, the way the photocenter accelerates and then lingers ties neatly to the phase of blueward and redwood shifts in the spectroscopy, a coupling that tightens the fit and fixes the inclination in a corridor that does not let the dark mass shrink into lesser categories. The long period suggests that the star and its partner have likely shared this duet for millions of years. Over such spans, small gravitational nudges from passing masses, from spiral arm potentials, and from giant molecular clouds can perturb a path. The persistence of the orbit's shape, despite these gentle tides from the galaxy, hints that the system's binding energy is strong enough to resist such weather. That strength grows with the mass of the dark companion, so the very survival of a wide, moderately stretched orbit in a busy disk becomes another small indicator that the unseen object is indeed very heavy. The long period also shapes where in the galaxy similar systems will be easier to find. Orbits that take years to unfold will be recognized sooner in regions of the sky that the astrometric mission visits often, and that ground spectroscopy can revisit across seasons without harsh weather or low elevation. This practical fact turns into a selection function that can be applied when predicting how many cousins remain unidentified. The line between discovered and undiscovered objects then depends as much on cadence as on mass, and the remarkable weight of this black hole becomes a calibrator for the fraction of the population that a given program can plausibly capture. The same cadence helps in a more subtle way by giving time to gather high-resolution images that rule out luminous interlopers. During the long, slow arc to apocenter, adaptive optics can peel back layers of crowding and confirm that the photocenter is linked to one bright star alone. During the slow seasons, deep radio and X-ray exposures can set ceilings on any faint accretion with low backgrounds. Every quiet non-detection that repeats over years turns what might have been a transient absence into a measured constraint. It is worth asking whether the long period can hide companions still more distant third bodies that add a slow drift to the velocities and to the sky path. In binaries with quick orbits, such drifts are easier to see, but here they could be subtle. The way to catch them is again through patience keep watching. If a gentle linear trend persists in the residuals after the two-body orbit is subtracted, the case for a far companion strengthens. As of now, the curves look clean within their error bars, a cleanliness that supports the interpretation that only one heavy dark partner shapes the motion. This simplicity does not banish curiosity. It refines it. Long periods also influence how these systems might evolve. Encounters in the galactic field can over great times torque a wide binary into a closer one, or the slow trickle of angular momentum exchange with small perturbers might reshape the eccentricity. In clusters, such processes run faster, but in the diffuse disk they run slowly, and the survival of this wide, quiet orbit suggests that such torques have been gentle. The system therefore serves as an example of a pathway in which a heavy black hole spends most of its life doing almost nothing observable beyond moving a star as if by a careful hand. This picture carries a final implication for the census that will follow. Binaries with long periods will continue to be harder to confirm individually, but they will be numerous, and each will add a distinct kind of weight to the galactic ledger, persistent gravitational unlit. The science that gathers them must commit to the same cadence they ask of the sky. It must accept that the strongest facts can take years to line up, and that in the interval, the absence of fireworks is itself a positive measurement. In such patience, long periods change from obstacles into signposts. They point to histories that lacked violence, to atmospheres that preserved memory, and to a class of heavy silent black holes that only a slow clock can reveal. Seeds of the heavy are planted by chemistry, mass and companionship, and Gaia Bh3 gathers those seeds into a few clear paths that must respect its wide, mildly stretched orbit and its refusal to shine. The first path is direct collapse. A very massive star born from gas with fewer heavy elements, loses less mass to line-driven winds, keeps a larger core to the end, and then falls inward almost at once. Little binding energy escapes as light, a small fraction leaves as neutrinos, and the orbit feels only a gentle loosening. A modest eccentricity can be imprinted by that sudden but limited loss, while the overall partnership remains bound. No great blast means no bright shell, no hot debris, and no large kick to twist or shatter the geometry. The present system, with its calm space motion, clean spectrum of the companion, and lack of high-energy light, fits this sketch with unforced ease. A second path is gentle binary exchange. Before death, the progenitor may have swelled and let a restrained wind cross the inner boundary without forming a luminous stream. The companion's surface would then carry hints of processed material without marked enrichment in elements that trace slow neutron capture. The orbit would remain wide, tides would be weak, and collapse that followed with little kick would keep much of the pre-collapse shape. The star we see today shows slightly lean metals and steady light traits that do not fight this idea, though the absence of strong chemical signatures keeps the exchange if it happened on the mild side. A third path imagines a merger of two massive stars before either one died. In a crowded nursery, tides and winds can drive a close pair together. The merged object, heavily mixed, can end as a single star predisposed to quiet collapse. If a distant third star survives, it can become the current companion. This route demands an early merger and an outer orbit that settled into the measured wide track. The data show no clear third body and no long drift in the residuals, so this path remains possible, yet unneeded. A fourth path invokes migration. The pair could have formed in a leaner chemical district elsewhere in the disk and later drifted to the present neighborhood through the slow churn of spiral structure. The modest, peculiar velocity does not forbid such travel. Under this view, the heavy remnant is a visitor from an older, thinner chemical suburb rather than a native of this one. Each path answers to numbers. The orbit says the newborn black hole received no large kick, because a strong impulse would likely have torn the pair or inflated the eccentricity far beyond what is measured. The distance and brightness place the companion away from infancy and away from a swollen elder phase, which argues against tides that would have locked rotation and smeared the lines. The chemistry leans toward fewer heavy elements than the local average without demanding great age. The continued lack of X-rays and radiolight during closer approach constrains any trickle of captured wind to levels too faint to matter. These statements together favor direct collapse with little kick as the simplest reading that uses the fewest inventions. Inside that favored path, details still matter. Neutrino emission during collapse removes binding energy and can increase eccentricity even without a visible explosion. The measured stretch is modest, a level natural to a small instantaneous loss rather than a violent unbinding. The system's space motion is warm but not extreme, which argues against an asymmetric impulse. Deep images and clean colors reveal no shells, no dust, and no odd absorption at the position which weakens the case for a recent blast. Rotation in the progenitor could have helped or hindered the making of a heavy remnant. Faster spin deepens internal mixing and can grow the core, but it can also drive equatorial outflows that bleed mass and angular momentum. The wide pre-collapse orbit leaves room for a middle ground in which rotation aided core growth without provoking strong shedding. The companion's calm rotation suggests that tides never lock the pair again in harmony with a broad orbit that changed little at birth. Magnetic fields, if present in the progenitor, could have coupled layers and redistributed angular momentum, suppressing late shedding while still feeding core growth. Such fields leave no direct mark now, but their quiet influence folds naturally into a collapse that ends without a bright show. Population thinking extends the argument beyond one case. If direct collapse is a common fate for very massive stars at lower metallicity, heavy, quiet black holes should be more frequent where older chemistry lingers. If metal-rich districts dominate wind strip more mass, and the remnant spectrum shifts lighter, eroding the ranks of long, silent binaries. Surveys can test this by mapping the rate of dark astrometric binaries against metallicity gradients that wrap around the disk. A higher fraction of quiet, heavy systems in lean districts would strengthen the case that winds and collapse physics are shaping the census that astrometry now begins to read. Demography adds a sober note. The initial mass function births far fewer giants than middleweight stars, so progenitors able to leave extreme remnants are rare. Time, however, is generous. Across the disk's long life, even a thin trickle of such births can stock an unseen inventory of heavy black holes that drift among field stars. Most will never flare. They will reveal themselves only by moving bright companions along slow ellipses. Gaia black hole. 3 shows that the gate to this inventory stands open to patient measurement. Formation channels that rely on later hardening deserve a glance. Distant encounters and slow torques can sometimes shrink very wide orbits, raising the chance of accretion or even late mergers. The present system shows no sign of such sculpting. Its long period and quiet spectrum read like a life spent far from disruptive neighbours. That calm makes it a cleaner test of birth physics, because later edits need not be invoked. All paths must also account for the companion's elements. Slight elevation in alpha elements relative to iron and overall lower metal content point to a natal cloud influenced more by short-lived giants than by long-lived sources of iron. That pattern makes weak winds in the progenitor more plausible and eases the route to a heavy core. The absence of strong signatures from slow neutron capture elements argues against a late heavy coating from an evolved donor. In the balance, the most economical story stands firm. A very massive star born from leaner gas lost little to winds and collapsed directly with small instantaneous mass loss and a tiny kick. The orbit stayed wide and only moderately stretched. The companion kept its shape and quiet light, and the remnant emerged heavy and mute. The other paths remain as graceful alternatives ready to step in should a distant third body be found, or a new chemical layer appear, but for now they are not required to explain what the numbers already say. What it means for the disk begins with weight, because gravity is the one certainty this system refuses to hide. A heavy black hole that does not shine still throws its influence across space, and when many such bodies are scattered through the Milky Way, they thread an unseen scaffold through the stellar disk. Each quiet remnant tugs on neighbours, warms orbits by tiny amounts, and adds to the slow thickening of the thin layer where most bright stars live. Over many millions and then billions of years, these gentle pulls build into measurable differences in how stars drift above and below the plane. The familiar rise of random speed with age becomes not only a record of spiral arms and giant clouds, but also a ledger of invisible masses that never light a lamp. The system at hand argues that such masses include a population of the heaviest stellar black holes, born quietly from very massive stars that kept much of their weight and fell without a roar. In that picture, the disk is not only a sheet of luminous points and gas lanes, it is a web padded by dark knots that are few in number but large in consequence. The first consequence is kinematic. In districts where the number density of quiet heavy remnants is higher, the velocity dispersion of ordinary stars should climb more quickly with age. The effect is not a jump but a change in slope that reveals itself only in large samples when stars are binned by both age and chemistry. Stars born from leaner gas, which often float a little higher above the midplane, may have shared neighbourhoods with more quiet remnants, and the extra heating would help explain why their vertical motions look warmer than those of richer populations of the same age. A growing census of heavy silent binaries will allow models to replace a uniform stirring term with a measured field of hidden perturbers. The second consequence is structural. Spiral arms and bars sculpt orbits, but they do so against a background of small gravitational nudges that roughen streams and weaken clusters. Open clusters dissolve as members trade energy during close passages. A sprinkling of heavy dark bodies along a cluster path can hasten that evaporation by pushing borderline members over the escape edge, leaving tails that spread more quickly along galactic orbits. When researchers try to rewind the positions of surviving clusters to learn where they were born, they must include scattering by unseen masses, or else the rewound tracks will be too tidy. The wide calm of systems like this one also touches the future of compact pairs. Binaries that begin wide and quiescent can be nudged by long-term tides, by gentle torques from the galactic potential, or by rare distant flybys moving a small fraction into tighter paths where winds and tides begin to feed. The quiet inventory thus acts as a reservoir for later episodes of activity, including in rare cases eventual mergers that announce themselves with ripples of gravity. If the reservoir is larger than assumed, then the rate at which the field supplies these late mergers will need to be revised upward, not because any single system hurries toward coalescence, but because patience transforms small probabilities into real events when multiplied by many wide pairs over very long spans. Chemical evolution inherits a subtler implication. Very heavy remnants formed by direct collapse return less iron and fewer heavy elements to the interstellar medium than explosive deaths would. In neighborhoods where quiet, heavy black holes are common, past cycles of enrichment would have been gentler, and that softness may echo in today's spread of metallicity at fixed age. The companion star in this system, with its leaner pattern of elements, becomes a small witness to that broader process. As the census of dark companions grows maps that tie the frequency of heavy silent remnants to the chemistry of field stars will test whether the heaviest remnants truly prefer the leaner districts, and whether that preference has left a measurable imprint on the present composition of the disk. Dynamics near the Sun is another arena where hidden mass matters. Streams of stars that peel from dissolving clusters hang in long filaments that curve through the local volume. They look smooth at first glance, but close inspection shows gaps and kinks that betray past encounters. A heavy black hole crossing a stream does not shout in light, yet its passage leaves a dent in the combined positions and speeds of the stream's stars that widens with time. If quiet, heavy remnants are part of the local inventory, some of those dents may already be recorded in the coldest nearby streams. Matching the number and size of such scars to the measured abundance of dark companions will tie a narrative of single systems to a cartography of the neighborhood. There is also the slow commerce of capture and exchange. A heavy black hole moving in the field may brush a very wide binary and swap partners, ejecting one star and binding to the other. Such exchanges are common in dense clusters but rare in the field. Still, over very long times, even rare events add up. The presence of a confirmed heavy silent black hole in a wide bond argues that some exchanges may have happened in the past and will happen again, slowly rewriting the network of wide pairs. Each rewrite changes the reservoir of future accretors and reshapes the chance that somewhere far ahead a once quiet pair will be driven into a brief active phase. Measurement strategy adapts in response. If quiet heavy remnants influence disk heating, stream texture, cluster survival and late mergers, then the most efficient way to constrain these processes is to count the dark companions directly, not only infer them. Maps of astrometric wobble combined with long baseline velocities become a dynamical survey of dark mass. As the count rises, the models that trace the growth of velocity dispersion with age can replace an assumed uniform, stirring with a measured mosaic of perturbers. As limits in high-energy bands continue to stay quiet, the case that gravity alone can mark the heaviest local corpses will sharpen, and the contrast between loud but lighter accretors and mute but heavier companions will become a central theme in how the Milky Way settles. The cultural picture inside astronomy shifts as well. The story of the galaxy grows less like a drama of rare catastrophes and more like a history of persistent background forces. Weight that never shines turns out to be a principal author of that history, drafting slow chapters on the shaping of arms, the loosening of clusters, the roughening of streams, and the timing with which a tiny subset of binaries are driven toward audible ends. The single system discussed here plays the role of a signature on that argument. It is not an outlier to be admired and set aside. it is a clue that the ledger of the disk is missing a column. Finally, there is humility. Acknowledging the impact of heavy silent bodies means accepting that the familiar disk is partly written by actors without faces. It does not make the sky darker. It makes it more complete. Each new ellipse traced in the motion of a bright companion adds another thread to the scaffold the eye could not otherwise see. With time, a layered map of light and motion will reveal a Milky Way where the seen and the unseen cooperate to shape every neighbourhood, and the old assumption that only fireworks build structure will give way to a steadier view in which quiet weight does most of the work. In that view, Gaia Bh3 is less a marvel than a measure, a standard weight placed on the scale of the disk, against which the gravity of everything else will slowly be compared. The next reveals do not depend on surprise, they depend on time. The European Space Agency mission continues to gather positions and motions, and with each additional year the small ellipse that marks the companion's path becomes more certain. A longer baseline shrinks the uncertainty in inclination and eccentricity, and as those angles settle, the mass of the unseen partner tightens within a narrower band that leaves little room for lesser remnants to hide. Future releases will also refine the parallax, shaving away the last sliver of doubt in the distance that underwrites the companion star's intrinsic brightness. The map of where the star truly is becomes as exact as the map of how it moves, and together those maps harden the gravitational case for a heavy dark centre. On the ground, spectrographs that are built for stability rather than spectacle add their own steady pressure. The very large telescope and instruments with similar precision continue to draw the slow breath of the star along the line of sight, not in a rush, but in careful cadence that fills the orbit's curve with points too numerous to ignore. The search for a faint second set of lines remains negative, and each season of nothing adds weight to the view that only one luminous body shares the dance with the dark. Near-infrared instruments that can peel apart crowded fields will return during the slow arcs to apocenter, to make sure that no faint ember is creeping close enough to bias the photocenter. The stage stays clean, and the orbit remains a geometry written in two lights, the light of the star and the light of motion. Across other bands, quiet watchers hold their posts. X-ray observatories listen during the closer bends, and radio arrays listen as well, ready to catch a stray whisper should the wind strengthen briefly. Their silence is part of the case. Each non-detection lowers the ceiling on any weak inflow, turning an absence into a boundary condition for how the black hole lives. Even a rare short flare would not overturn the story, but continued calm would carve it deeper. In parallel, surveys of many stars begin to look more like this search and less like a chase after fire. Astrometric pipelines learn to recognize long-period ellipses with small amplitudes without discarding them as systematic noise. Machine learning tools trained on confirmed dark binaries weight telltale combinations of features: a bright star with calm rotation, a mild lean toward lower metallicity, a clean field, a cadence that traces a slower symmetry between approach and retreat. Those tools pare down a large sky to a shorter list of candidates that deserve long, spectroscopic attention. The count of measured ghosts grows. Population models respond and sharpen. Simulations of the galactic disk that once assigned explosions and kicks according to older expectations recalibrate, setting more massive progenitors on paths that end in quiet collapse when chemistry leans to the thin side. The distribution of black hole masses in the models shifts heavier, and the output catalogues are then sent through artificial versions of the real selection pipelines to see how many would be found. The comparison between predicted and measured tallies feeds backward into the assumptions. The result is not a locked picture, but a living one, a cycle in which each new orbit solved in the sky edits the next round of model births and deaths. New methods step alongside the old. Precise photometry collected for planet searches and stellar oscillations supplies time series that, when combined with astrometry and velocities, can flag subtle line profile changes or minute brightness drifts that correlate with orbital phase. Polarimeters test for faint phase-dependent scattered light that could indicate a cool thin disk, even when accretion remains below detection in high-energy bands. Microlensing surveys contribute in the background, catching rare events in which a dark mass magnifies a distant star's light and then fades, adding points to the distribution of isolated compact objects that parallel the census in binaries. They do not identify companions, but they sketch the dark tail of the mass function from a different angle. Even gravitational wave astronomy, which listens to merging black holes rather than to quiet ones, finds its interpretation altered. If heavy remnants are more common in the disk than older models, allowed, a portion of distant signals may trace back to long calm histories that only later tightened under gentle torques. The rates of such channels will be revised, and the physics of black hole birth in lower metallicity gas will sit nearer the center of those revisions. All of this activity turns a single labeled system into a fulcrum that shifts the wider field. It also changes technical culture. Archives of radial velocities once kept for exoplanet hunts become mines for dark binaries. Meticulous calibrations of astrometric systematics, once seen as internal housekeeping, become the enabling craft of discovery. Even the rhythm of observing proposals changes as committees learn to weigh the promise of long steady programs against the glamour of fast transients. This sky, after all, is not only a theatre of shocks, it is a clock that reveals weight by keeping time. In the nearer term, the very system that sparked this change continues to teach. As the orbit fills, small deviations from a perfect two-body motion can betray an even more distant third body, or a slow drift that hints at large-scale galactic tides. If none appear, the emptiness will be data too, because it will confirm that the simple portrait is exact, and that the heavy object can be weighed without hidden hands at the scale. The companion star will continue to serve as a standard for how low metallicity signatures look in such pairs, allowing comparative studies to be made across the sky. The lack of any hot gas signature will remain a measured boundary for models of wind capture at low densities, anchoring calculations that must otherwise work with poorly constrained flows. Nothing in this program asks the sky to shout. Everything asks the sky to be steady. What it means for the Milky Way is that the largest local weights will be read by their footprints on the paths of ordinary stars. What it means for the idea of discovery is that patience becomes an instrument as real as any mirror. Gaia Bh3 is therefore less an endpoint than a standard candle for the dark, a quiet measure against which many future measures will be compared. The next reveals will come as ellipses that close as error, bars that narrow as catalogues that lengthen, and as models that yield to the most modest of demands that gravity be allowed to speak by the slow motion of lightless mass through lighted space. The Milky Way turns, and the European Space Agency mission keeps its slow count. A bright star wavers the way a hand trembles when it carries a hidden weight, and from that tremble a map grows in which darkness gains coordinates. The radial lines in a spectrum breathe in and out. The orbit draws its ellipse without haste, and the absence of hard light becomes a signature more durable than any flare. The companion's elements whisper of a leaner birth cloud. The wide path holds its shape across seasons. The heavy centre never shines. Together, these facts write a page that the field has waited for, a case where mass is measured by patience and where silence is the most reliable instrument. Around that page, the larger book opens. If one heavy, quiet remnant waits behind an ordinary star, then many more may sit in the drifts of the disk, turning the background of the galaxy into an unseen scaffold. Streams gather small dents where dark bodies have passed. Clusters loosen sooner in neighborhoods enriched by weight without light. The spread of stellar speeds with age thickens subtly, a sign of stirring by hands that never glow. Each measurement refines a census that once knew only fireworks. Each non-detection in high-energy bands hardens a limit. Each season added to the astrometric curve turns a faint suggestion into a practiced line. None of this ends. The orbit will continue to turn without hurry. Spectrographs will continue to write down the calm breathing of a single star. The catalogue will stretch to include cousins. The models will bend to fit them without drama. At the centre of it all remains a simple truth. Gravity is patient, and patience is how it is heard. A heavy body rests where it has always rested. A bright partner keeps time around it. The galaxy carries on its visible light, stitching a net over a sea of weights that do not shine. And in that quiet expanse, Gaia Bh3 is both landmark and guide, a point the night returns to as it teaches that the deepest stories are sometimes told at the softest volume.